It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on mechanics of unsaturated soils, which will be delivered by Professor Emeritus Delwyn G. Fredlund and Dr. Murray Fredlund. Dr. Fredlund received his training from the University of Saskatchewan and Texas A&M University and has published over 50 research papers on topics related to database design, finite element modeling, and unsaturated soil knowledge-based systems. In 1997 he started Soil Vision Systems Limited with a database software product called Soil Vision which could be used to estimate unsaturated soil behavior. He has since directed the development of 8 finite element software packages covering areas of groundwater flow, contaminant transport, geothermal analysis, airflow analysis, stress deformation, and slope stability. More recent work has involved supervising the development of the 2D/3D SV slope stability software and the SV Designer conceptual modeling software. This work has continued with the expansion of 3D slope stability analysis into the areas of mining such as the analysis of open pits, tailings dams, power dams and performing landslide risk analysis.
So thank you so much, Professor Das and Partha and team for organizing this event. I'm happy to be here and talking to you today about numerical modeling of unsaturated soil problems. And what are we going to go over today? I'd like to give a little bit of a background of the area, and just focus really on what is the problem. There were a few questions that related to this on what is exactly the issue with unsaturated soil mechanics as opposed to saturated soil mechanics, and why should we be using unsaturated soil mechanics. So then I'll talk a little bit about the 2 main areas that we do numerical modeling in unsaturated and saturated soil mechanics, that is seepage modeling and slope stability. So we'll talk through some of those, go through some maybe example applications, and then give a bit of summary for the area, what we've learned so far. So saturated soil mechanics is commonly utilized in practice, as has been mentioned by some of the people commenting. And the assumption is that saturated conditions represent a conservative design case, i.e. a large rainfall event could possibly reduce suctions to 0. And so typically our numerical analysis ignores the effects of soil suction and focuses on a total stress or effective stress analysis. But the problem is in some cases, what if the saturated approach is not realistic? Or when will a saturated approach not represent a conservative approach? Can costs of unsaturated modeling be reduced? And what are simple methods of applying unsaturated soil mechanics in practice, in our numerical modeling specifically? So before we get started with this, maybe let's proceed with the first poll, which just states what percentage of cases do you consider unsaturated soils in your numerical modeling, just to give a bit of an idea of where we are with the industry. There we go. Interesting example, very interesting answers here. It sees, we see with most people, the most common answer was about 30%. So interesting. So let's keep going here. So it is a significant problem if we're hitting it about 30% of the time. So let's talk first about seepage modeling, unsaturated analysis. So just as a refresher, we have really 2 approaches. We can do steady state modeling or transient state numerical modeling. In steady state, time is infinite. The right side of the partial differential that Dad showed has our storage equation, and it's equal to 0 in the steady state condition. Boundary conditions don't change with time. And water entering or leaving the model is identical. Therefore, the change in storage becomes 0. And the SWCC definition is not required since the change in storage is 0. And saturated and unsaturated hydraulic conductivity, however, is required. Now, if we move to transient state, On the other hand, we consider time, and both sides of the equation come into play. Hydraulic conductivity and soil water characteristic curve functions are required as model input, and the zones are modeled as continuous. So there's a lot we can do with this. This just gives an example of the facial modeling example, in which case we looked at a tailings dam, and we modeled the saturated and unsaturated seepage of this scenario in a detailed 3D way. And we can look at the latest techniques of modeling chimney drains and thin layers, and how does unsaturated seepage play into this? And what about climate? How does that apply? And much of this is laid out in the public study that is noted. But here we have a good example of unsaturated seepage analysis and its application to practical cases of modeling tailings dams in this case. So let's back up. We've showed a complex 3D example. Let's back up and just talk one-dimensional seepage flow, just to remind everybody that really we're looking at if we have a water table and we're only considering vertical flow, then we have a hydrostatic line leading up to a covered material, let's say our covered ground surface. Then we could potentially develop hydrostatic conditions. However, that doesn't usually exist in real life. So we have infiltration that happens, a rainfall, and that tends to pull our pore water pressures over to the right. So you're moving from line 1 to line 3. And if it rains long enough, you will saturate the whole area and your groundwater table will move up to the surface. But most of the time that does not happen. Because the rain stops, and then you enter into a period of evaporation, and it pulls the suctions out to the left, and it pulls the hydrostatic line to the left, and flow is generally up. So on the right-hand side of hydrostatic, flow is down, left-hand side flow is up. And so it's a simple way of seeing how a lot of times we need to understand this flow, number one. Number two, how does it contribute to the water balance of our seepage modeling? Is it significant? And by not considering it, are we creating some difficulties? So as mentioned before by Dad there, here's the main partial differential equation for seepage modeling, both saturated and unsaturated. And you have your coefficient of permeability, which can be a function of soil suction in multiple directions. Then you have your head variable to be solved, and on the right-hand side, you have your change in water storage in with any element and the accounting of time. So this is the partial differential that we're solving. And as input, you need to put in your soil water characteristic curve. And that's what we put as users into the software. However, the software differentiates that curve, and what the finite element algorithms see are the change in storage versus suction. So this curve is very important, and anytime you have peaks like this, it can be a potential problem to move around in finite element equations. And then you need your permeability curve, which describes how permeability or hydraulic conductivity decreases as suction increases. And ideally, your air entry value lines up between, well, it must for all of these three curves. So this is what you need to set up seepage. How do you get these curves? Well, Dad mentioned and went through some of the methods of measuring this in the laboratory. There's also ways of estimating this and calculating these curves. So we have a product, SV Soils, that can be used. It has a database of over 40,000 unsaturated seepage soil water characteristic curves. There's 9 methods for estimating the soil water characteristic curve. There's 6 theoretical methods for estimating unsaturated hydraulic properties. So a lot of times, if the budget is somewhat limited, then you can make use of estimation methods. So in this case, you can data mine the database for similar soils, or you could use one of the methods for theoretical estimation of the soil water characteristic curve. So these are methods, and people have often said, well, I'd rather measure it in the lab to be sure, and that is the best method. However, there's some interesting studies that have come out previously that where they have tried to match, or they've tried to estimate the variability of measuring it in the lab, because you have different personnel, you have different equipment, you might have different testing procedures. And what they found generally is that the variability experienced in a lab for measuring the soil water characteristic curve is about the same as the variability that you would experience in your theoretical estimation methods. So sometimes we can get a reasonable theoretical estimation of how our material will perform in the field just by doing a theoretical estimation based on a grain size curve. And so a lot of times that can be good enough. And the unsaturated hydraulic conductivity curve, there are some curves in the database. This is a more expensive curve to measure, more time consuming, and therefore there's fewer curves that are available. And most people that do seepage modeling estimate this curve anyway. So if this was easy to do, everybody would also do it too. There is a number of common issues that people run into when they're trying to model unsaturated seepage. And we just want to go through some of these, because they're typical and they're common. They're not fringe problems. For example, if you just modeled flow into a dry soil, which is the animation shows here, you actually have a very nonlinear problem that you have to solve, in that the water comes down, it hits a dry surface, and it flows down through the unsaturated zone to a water table. And in this case, what we've done is we've looked at this particular problem, and we've turned on mesh refinement to try to track where the nonlinearities are happening in this model. And I'll just start the animation here. You can see that. You can see that as the wetting front progresses down into the soil, the mesh, the location where you need mesh changes. And this is very important because you need to still maintain your numerical accuracy as your infiltration front is moving down through the soil. And you can see the water table then rising up through this. So this is a very simple problem, and it can be very challenging to solve and very nonlinear. And so a lot of people, I mean, the first time I tried to set up a numerical model in the lab, that was years ago, I tried to enter it and I got everything all set up and the finite element mesh all set up and pressed go, and I had convergence problems. And so of course, not with our software, this is years before I made it, but it's very common to hit convergence problems with highly nonlinear unsaturated flow models. And there's strategies though for fixing that. And we want to talk through some of those strategies here. Particularly, transient problems are sensitive to the maximum slope of the soil water characteristic curve. So the easiest soils to model are the soils that have the least steep soil water characteristic curve, which are more clay-based type of materials. So if you have clays, they're actually the easiest type of materials to model numerically. Once you get sandy gravels and you get a steeper soil water characteristic curve, what that does is that creates an increased spike here in this curve in your water storage function, and it becomes progressively more difficult to model. So some people try to flatten a steep curve and the unsaturated hydraulic conductivity curve to make their model converge. However, then you're moving away from the realistic conditions, is the bit of the difficulty there. You can also steepen the soil water characteristic curve, and the permeability in a staged-wise analysis, we allow this in the software where you can slowly stage in and start from more conservative conditions, and in a steady state problem, you can move towards your actual material properties in stages, and it preconditions the solver with each stage setting so it converges much better. And you can also perform a transient analysis with reduced time stepping as another strategy. So there's methods around these problems. So another issue that people often have is that your soil water characteristic curve slope goes to 0. So if we just enter a soil water characteristic curve into a seepage problem, it differentiates it and it produces a water storage function, which is shown in the lower right. However, there's a strong tendency for that one to go to 0 on the left and on the right sides of that equation. On the left, we essentially cut off that equation at a certain suction and give it a minimum slope to overcome the issue of it going to 0. And on the right-hand side of the equation, some equations tend to flatten off and go to 0. For example, the Van Genoegden equation and Mullum and some other equations go to a flat condition, which at higher suctions can create some numerical instability if you hit suctions that are higher and your slope goes to 0. So in this case, additional equations like the Fredlund and Zing go to 0 at 1,000,000 kPa, but they keep that small slope through this zone, which actually greatly enhances the numerical stability of your finite element software in these zones. So these are other ways you can alleviate issues. It should also be noted, we often do seepage modeling, and we enter a small slope at the start of our soil water characteristic curve. And there's a small value. Many people, I think, skip over this parameter because they're not entirely sure what it is, and they enter either a default value or they put a value that will converge. But this value is significant from the sense that what it does is it gives the slope of the storage curve in the positive pore water pressure zone. You can't fully plot this. I've just illustrated it here graphically, because you can't plot log and arithmetic scales together here. But if this number gets too small, it means that there's a fairly large slope out in the positive zone. And on larger problems, say if you have a facility that is over 300 feet tall, putting in initial slope of 0.01 indicates a change in your volumetric water content, or your porosity down at the base of your problem, of about 1.0. So your volumetric water content goes from 0.48 to 1.48 and essentially creates water in your model. And so this slope should be much smaller to avoid this type of scenario. In terms of permeability, seepage analysis are very sensitive to the slope of the unsaturated hydraulic conductivity curve and the minimum. So which estimation is best? We provide a number of ways to estimate this curve. Generally, it falls off with unsaturated conditions, which is okay. However, the air entry value should match the soil water characteristic curve, and your absolute minimum should be defined and not be too small. A typical case that is problematic is where your unsaturated hydraulic conductivity curve goes to 10 to the minus 15 or 20 meters per second, which is physically unrealistic. If you look at the vapor flow, vapor diffusion rate, it's tagged at about 10 to the minus 12 or minus 14 meters per second. So once you're down that low, you should have a minimum of about 1e to the minus 12 meters per second. And therefore, if you cut that off, which the software allows you to do, you will alleviate a lot of numerical convergence problems with modeling high suctions in unsaturated problems. So there are workarounds for these type of problems. So in summary, we can use estimation methods to reduce laboratory costs for unsaturated soil modeling, and they've proven to be quite effective. As well, strategies exist for handling nonlinearities of numerical analysis and allow processing of larger models like this. I just show this because this is an example of Oroville Dam, which it was one of the tallest power dams in the US, and there was unsaturated seepage and slope stability modeling performed on this earth structure. The geometry was quite complex. However, the software was able to handle this in this case. And so it is quite admirable what we are able to accomplish in terms of numerical models, especially in seepage modeling at this time. So just another poll question before we keep going here. So number If we can, I guess, throw this up. What is hindering our application of unsaturated soil mechanics in practice? It's always interesting to see what people feel and get these questions answered. That's interesting. Okay, that's probably good. Yeah, so 67% say more teaching needs to happen on this subject. So that's very interesting. It's good to know. So let's keep going here. So now I'd like to talk a little bit more about stability and the application of both 2D and 3D stability analysis. And we're going to talk primarily about 3D today here. So 3D limit equilibrium method of columns is an extension of 2D method of slices. And if you compare 2D and 3D analysis, you will have differences between 2D and 3D in the order of somewhere between 10 and up to 60, as high as 60% difference between a 2D and a 3D analysis. And some studies have shown that ignoring 3D effects can result in an overestimation of in situ shear strength. And just some of the studies. And the influence of negative pore water pressures has generally been ignored. A study done by Chung in 2004. So we're going to talk through some of this and look at a little bit of 2D, 3D effects and some unsaturated effects. And for doing 3D or 2D analysis, there's very well developed commercial software packages available to do either 2D limit equilibrium, apply unsaturated soils in it, or push that to full 3 dimensions. This was a tailings dam that we did a previous webinar on. It was quite complex geometry, and we showed how to analyze this. So the ability of the software now to handle fairly large problems is quite admirable. So, and our ability to, in particular, model 3D problems, a lot of users have said that, well, it's difficult to construct in 3D space. And new techniques are being developed all the time. This is one new technique that was just released as a trial feature in our software, where you can take multiple cross sections, as shown in the upper figures, and you can stitch them together, essentially with splines, and match up the vertices and build full 3D problems very quickly. And so there's, just bring this out to say that the barriers to doing 3D analysis are quite small now. You can set up these models quite quickly in a matter of a few hours or a few days and analyze them very effectively. So, but we still have to get the physics right, even though we can do large 3D models. And so it's worth talking about the unsaturated suctions and how do we account for unsaturated conditions in a numerical model? So number one, can suctions be maintained in the soil? And I like this figure because it shows really our hydrostatic line here. Here's hydrostatic condition, here's our water table. And in this case, we're raining on the soil at a rate that has a moisture flux that is less than the saturated hydraulic conductivity of the soil. And there's a perception that if we rain on soils that it will always destroy suctions all the time and for the full depth. And that's not actually quite true. What will happen in this case is that if you rain at a rate that is less than the KSAT, you will equilibrate at one of these vertical red lines where you are meeting your flow into your model is enough so that the flow is being allowed to come in. However, it will continue along this forever, and soil suctions will still be maintained in the soil. And that's essentially what happens at the in the Hong Kong slopes that Dad mentioned, is that it can rain and it won't rain enough to fully destroy soil suction. So there's still enough suction to keep a slope stable over time. And rain can go on for a very long time, and the slope still has suctions and still maintains stability. So it's an interesting effect that we should be aware of. Then there's the case where the flow into the model is higher than the KSAT. So it's higher than the ability of the soil to accept that moisture. And so what we have in this case is the concept of more of a wetting front, where suctions are destroyed completely, but it takes time for this wetting front to go down through the soil. So the rainfall typically has a length. Even a big surge in rainfall will only last for typically a few hours. And you'll get a wetting front that progresses down into the soil, but it will not have the ability to destroy suctions all the way down to the water table. So you get kind of a zigzag formation of suction. So in this case, you destroy suctions on the surface and near the surface, but you still don't destroy them deep. And that's where your stability comes from. So in 3D method of columns, it's just an extension of 2D analysis. And really, we have some extra physics we have to deal with. On every slice becomes a column now. And we still are solving the same equations for moment and force equilibrium here. And just to point out that here's our shear strength equation on the top, tan phi and cohesion. And really, in unsaturated soil mechanics, this effective stress, the tan phi becomes has an extra cohesion component called tan phi b, or based on physics of a different method, but it's still accounted for in this equation. So, and all of these are programmed into the SV Slope software there. So one thing I should mention and just clarify, because we get technical support, and people have said in the past, well, I'm applying soil suctions and I'm applying different pore water pressures and my factor of safety isn't changing. And inevitably what's happened is that they have put in negative pore water pressures or suctions into their model, but then all of their materials are more Coulomb constitutive models that they've utilized. So if this is the case, then really your more Coulomb has no ability to consider soil suction. It only considers effective stress. And so you have to have two things, is what you have to remember to consider unsaturated soil mechanics in a slope stability problem, or slope stability model, I should say. You need suctions and you need an unsaturated constitutive model. And there are about 6 of them implemented in SV Slope right now. You could use any one of them and they will consider the influence of suction on your shear strength in different ways. So probably a good time to stop for another poll question. Why don't we throw up this one? How much can unsaturated soils typically affect the calculation of the factor of safety? Because I'm baiting you with a question, because we're going to see what the audience has to say, and then we're going to go through some real world case studies. All right, so 49% of you guessed that it's greater than 15%. So we will see if you're right about 20% on each 10% and 15% answers. 3 and 4 each got about 20% vote. And so we'll see where this leads us here. So let's first look at a low angle slope. And this was interesting research performed by Chung back in 2004. And what she did is use the phi b representation of shear strength, which is probably the most simple representation of shear strength. It's one of the earliest ones proposed, and phi b can be a percentage of your phi prime. And what Chung did is she had 3 different water tables in a simple slope, change in the water table, and looked at the influence of the suctions on the factor of safety. So if we go forward here, I'll just take a little bit to explain how she plotted the results. On the left-hand side, we have the difference between 3D and 2D analysis. So in other words, at 0%, it means that 3D gave the same factor of safety as 2D. And so those of you that have listened to other talks know that the difference between 3D and 2D is that 3D is typically a higher factor of safety. It'll almost always be higher. It's just a matter of how much. And so in this case, on the lower axis, we have phi b divided by phi prime. So in other words, phi b is 0 over on the left-hand side. And what this means on the left-hand side is we're modeling it as a saturated case only. We're only considering phi prime. On the right-hand side, on the far right of the graph, where the horizontal axis is 1.0, we are considering that phi b is equal to phi prime. So in other words, soil suction contributes as much to the strength as net normal stress. So we are, as you can see, as you move from left to right, there's a general trend upward from left to right. The average distance, or the average difference between 2D and 3D, is between 6.2 and 15%. And the ability of unsaturated suctions to influence the result is about 8%. So it makes a little bit of a difference on your model and your consideration. So just if we plot the friction angle versus cohesion for different combinations, really we see the difference for a low angle slope. The difference between 3D and 2D analysis is between 9 and 16%. So fairly reasonable. And this is considering a phi b of about 15 degrees. So it includes the effect of matrix suction in these answers. So now if we consider a steeper slope, here we have a 50-degree angle on this, typical material properties, and we're considering again using phi b and changing the groundwater to 3 different elevations through all of this. And of course, the critical slip surface location can change as the water table is changed as well. So here we have the results presented, again, same graph, and you can see they vary between as low as about 7–8% and up to over 20% difference for different conditions as you change. Like there's changes as you go from 2D to 3D and as you increase the influence of soil suctions from left to right. And you can see the influence is interesting. So there is overall definitely a difference. And if you chart this versus cohesion and friction angle, you can see that really your difference between 2D and 3D ends up being between 15 to 18%. And this is at a phi b of 15 degrees for your friction angle for suction contribution. So reasonable differences, and enough that you'd probably want to consider this and know what your answer is. Previously, I should mention that when we've designed slopes with factor of safety, what we've done is that we have just assumed that, well, we won't do it in 3D, we use 2D because I know that 2D is conservative and it helps me. But why not know what the difference is so that we can actually plan for it and design for it? And that's really what 3D modeling is about, is bringing your model closer to reality and eliminating some of the unknowns that we have always known are there, but we just didn't know what they were. So this just also talks as well with this next slide is modeling geometry changes. So here is just looking at a concave or a convex slope, and these are simple examples, and I like these because you can wrap your mind around them quite easily. They're examples that you cannot model in 2D. In other words, you can't model a crease in the 3rd dimension in a 2D plane strain model. So what is the influence of change in the geometry, convex or concave? Well, you can see here, and this is just one case we looked at, and one of the more extreme ones is our factor safety in 2D is about 1.8. If we model this in 3D, factor safety jumps up to about 2.9, and this is considering unsaturated soils in this model. So a change overall of about 59%. So you're getting into a range where you're looking at the combined effects of geometry and unsaturated soil mechanics, and you get quite a significant change between 2D and 3D. And so in this case, suction drives the critical slip surface deeper is what happens, has to be remembered. So the differences can be quite significant. So this graph summarizes some of the differences between concave and convex analysis conditions. So here's the corner angle at the bottom. On the vertical axis is the difference between 2D and 3D. And the red line, in the red line, we're considering phi b equals to 0. So in other words, we're considering that there is no change, no influence of unsaturated soil conditions at all. And what we're looking at is the difference between 2D and 3D purely from geometry, considering saturated conditions only. And you can see that as you get more convex, then your difference becomes quite great here. You're up at about 35% difference between 2D. Whereas if you consider your unsaturated soil mechanics, you get a bit of a different curve. And that's between 12 and up to 59% difference between 2D and 3D, considering unsaturated soil mechanics, which is blue, and 2D, 3D effects. So you can break out the different effects of different analyses, which is quite interesting, I think. So the unsaturated shear strength envelope is controlled by two main variables. So how do we estimate the unsaturated shear strength of the soil? And as mentioned, there's about 6 different methods in the software, which we can make use of, thank goodness. But this just gives a rough overview of them, the physics. We have the air entry value and residual conditions. The 2 pivotal points make the unsaturated shear strength make a nonlinear, essentially, envelope. Deviations from the effective angle of internal friction start at the air entry value, and it's difficult to justify relying on a further increase in shear strength beyond residual suction conditions. In other words, once you hit residual conditions, there's not enough water to provide tension in the water phase to influence the shear strength. So these 2 curves do a lot to illustrate this. On the left, we have our soil water characteristic curve, and the air entry value is hit and the soil rapidly desaturates to residual conditions. And on the right-hand side, you have a corresponding shear strength envelope. And so let's just talk through what happens here. Is that on the left-hand side, on the shear strength equation, you have, before the air entry value, you have your phi b equal to phi prime. And therefore, your contribution to shear strength from the soil suctions equals your phi prime. Then as the water desaturates, your shear strength will typically fall away from your phi prime angle. In other words, it can't contribute as much because there's not enough water to pull on. And then once you hit water residual conditions, you can either decrease, or if you have plastic clays, you will still maybe hold steady or slightly increase. If you have more cohesionless soil sands, your shear strength will typically decrease after the residual suction has been reached. And so it gives you an idea of the general. Most of the equations implemented in SV slope roughly follow that general concept. And so here is just showing different shear strength functions in SV slope plotted as a function of soil suction. And we can see that they have different shapes to some of these curves, and up to the air entry values, a lot of them are more similar, but after that they diverge some. So you can see the general format of these equations here. So if we summarize this, the influence of these equations, and here we're plotting the factor of safety versus the air entry value of our soil. So in other words, we're moving from, if you can think of it, we're moving from more sands to clays as we go left to right, because the air entry value of a clay might be about 100. Air entry value of sand is maybe about 2 or 3 kPa. And so we're moving from left to right, from sands to clays. And then what is the influence of if we have suctions in that material? You can see the blue line is really phi b equals 0. In other words, we're not considering any suction influence. Phi b of 15 is the green line, and phi b equal to phi prime is the red line. So phi b equal to phi prime is a nice boundary, because that really defines the maximum influence possible by suctions. It can't be greater than phi prime, and so that's our upper bound. And so what you're seeing as you go through these is the different material shear strength functions that are proposed by different researchers. And what you're seeing is that as the suction, the air entry value increases, it's raising the factor of safety because we're considering the influence of suctions at higher suctions, and it's raising the factor of safety. So this I find is a very interesting plot to bound the potential influence of soil suctions on factor of safety. So what we have found, what Chung found rather from her study, is that when air entry value is smaller than 1 kPa, really that's your sands, the effective matrix suction on slope stability is quite trivial, and it's probably not necessary to include it in your analysis. If we have an air entry value between 1 and 10, then we can use nonlinear estimation equations to estimate shear strength. And a value of 15 degrees is not really a conservative assumption. If it's between 10 and 200 kPa for air entry value, a phi b of 15 degrees can be assumed for unsaturated shear strength quite effectively. And for air entry values greater than 200, phi b can be assumed to be phi prime. And so just ballpark recommendations for applying this in unsaturated soil mechanics in practice. So how does this play out in a typical analysis? So let's look at one case study that is the Poplar River Mine highwall failure. It's well researched. This was first published by Clifton and others in 1986 and Lamb and Fredlund in 1993. So long time ago. And what to describe the problem, this was there was a drag line at a mine site. It was situated about 20 meters back from the crest. And they were operating the drag line, pulling material up the side slopes. And they noticed cracks forming behind the drag line. And they did further investigation. And they realized there was a slip surface starting to develop. And they were able to roughly measure where that was located. It was close to failure. And there was a sloughing wet sand partly down the slope that was contributing to a lower shear strength area. And so this came close to being a major failure. They were able to get the drag line off before it failed, is what I understand. But what's nice is this was close to failure, and it's a very three-dimensional problem. So the original work was analyzed in 1986 by doing a back analysis in 2D. And then in 1993, Lamb and Fredlund analyzed it in a three-dimensional method. And we did some further analysis on this with SV slope and more modern computational methods. And we could analyze this, set this up and analyze the 3D soil mass that moved here. And this is just showing it, and we've exploded the sliding mass out of the slope and shown and projected there's the location of the drag line, and we've applied a load equivalent to the drag line on top of the 3D model. And so really here what's interesting to note is this, is on the bottom red line, first of all, this is the factor of safety on the left-hand side. So because it was close to failure, theoretically you should be close to 1.0. So the original analysis focused on bringing the factor of safety for the 2D analysis close to 1.0. But then there's the influence of unsaturated suctions because the water table was quite low in this case. So as we're going left to right, what we're doing is we're increasing, considering unsaturated soil conditions up to 75%. So if you do this analysis, you get something close to 1 for the 2D, which is close to benchmarking it, and you back out material properties. But the difficulty is with this, if you do this problem and you analyze it in 3D, you get quite a jump in your factor of safety with the same exact material properties. And so that creates a bit of a problem because this line is much higher and it gets worse, up to a 90% difference if you start considering unsaturated soil mechanics. And in reality, the slope was failing. So you would have to and the best way to model this is to take the 3D model and weaken your material properties till this blue line drops down pretty close to 1.0 factor of safety. So this is, we didn't have time to do that in this case, but it's an interesting thing to note. If we had to do that, we would have to weaken our material properties, and the material, what it implies is that the material properties were actually weaker than what was thought at the site. And so this, it's back analysis should really always be done in 3 dimensions, and it otherwise it can yield non-conservative results. And if you use back analyzed properties in 2D, it can result in you thinking that there's more strength there than there actually was. So some conclusions we can draw from this are simple slope angles. The difference between 2D and 3D factors of safety increases from 9 to 16% when phi b is 15 degrees. For steep slope examples, the factor of safety varies from 12 to 18% when phi b is equal to 15 degrees. Concave geometries and changing geometry, we can see that the difference between 2D and 3D factor safety can vary between 20 and 59%, which is quite significant when we consider unsaturated soil mechanics. And back analyzed shear strength parameters can overestimate your shear strength by 71 to 90% when you consider the unsaturated zone in the physics. And one of several estimations of unsaturated shear strength provides an improved simulation for slope stability analysis. So we have different methods to estimate unsaturated shear strength. So in summary, unsaturated soil mechanics can be considered in current commercial software packages quite effectively, and it opens up applications for practice and further research on the subject. And unsaturated properties can be estimated with reasonable techniques quite easily, for that matter. Climatic and unsaturated flow can significantly affect stability in earth structures. And back analysis without considering unsaturated soil mechanics can be non-conservative. And so that concludes the talk here. And just a last poll that we'll put up there. And what percentage of industry problems do you see a need for application of unsaturated soil mechanics principles? Okay, we see that more than 52% felt that 50% or more of industry problems have unsaturated soil mechanics principles there. And so lastly, I've enjoyed very much talking to all of you. And just here's some contact information if you want to contact me, if you have further questions to follow up. Myself, or if you click on the sales link, our Bentley team can help you in seeing if you already have a license to Bentley software, or help you in acquiring a trial version. You can download a 7-day trial from the Bentley website, and we'd be happy to answer further questions and relating to the software. So thank you all very much for your time. Okay. All right. From Sebastian, is the adaptivity available to all soil mechanics parameters such as shear, deformation, and so on in the SV soil software? And so you can model, you can represent shear strength and triaxial material parameters in the SV soils. You can also represent the soil water characteristic curve and the shrinkage curve. You can represent it, but yes, you can't. There's more functionality with some of the unsaturated soils functions than in the shear strength, but you can represent all of those tests in the SV soil software. So another question here. What is the most reliable software to be used for slope stability analysis of unsaturated conditions? So being as I make the software and I control the quality from start to finish, our team does in Bentley, I would have to say our own software. I'm not sure what else I would say, but we feel it's the software overall, I would say, has become very reliable. There's great QA, QC procedures for heavy testing of the software during the release process. So as far as I'm aware, maybe I can put it this way, the unsaturated functions in SV Slope are the most extensive of any software package currently available. So maybe that's a way of putting it there. Another question. Calibration is a key component of numerical simulation. I would agree. Do we need to monitor suction in the field? Do we need to in situ measurement of the unsaturated zone? Yes, this is a common question. The answer is yes, but it's difficult. It's a little more difficult to measure the changes in soil suction above the water table. And this is often forgot of. Like, we put in piezometers and we measure groundwater fluctuations, but for example, there's been proven cases where the groundwater table is almost stable in a slope or in some kind of earth structure, and yet you get a big rainfall and it wipes out the soil suctions and you get a gigantic failure. So in that case, you're not even seeing your changes in soil suction. So the use of lysimeters, trying to get your net flux through into the water table, is one method. People have drilled boreholes and gone down and tried to take samples out and measure them for water contents and suctions to try to establish monitoring of suctions and water contents in the unsaturated zone. But if you have a large unsaturated zone, and maybe a way to do this is to do it through back analysis, is model it and find out what the potential influence is if you include soil suctions or you don't include soil suctions in your numerical model. And you should be able to see if that makes a 5% or a 10% or a 25% difference in your factor safety calculation. And then you can use the modeling to guide how important it is to model your soil suctions in the unsaturated zone. Maybe that's a way of approaching it. What are the additional input parameters commonly required to model unsaturated soil problems over the saturated one? Well, if you are estimating them like we talked about, then you just need grain size, and you can estimate your soil water characteristic curve, and then you also are recommended to measure your saturated hydraulic conductivity, and then you can estimate your unsaturated hydraulic conductivity from your soil water characteristic curve. So really, you could get away at the very minimal with just having a grain size and a KSAT value, and you could model full unsaturated soils. That's the shrinkage curve, as Dad talked about, is also then important if you're stepping it up a notch and doing more detailed modeling. So what simulation software do you suggest to me if you have to simulate the change in degree of saturation when air is injected into the soil? Well, we've used our SV Flux software significantly on many problems. The key component here is when air is injected in the soil. So to model this problem, you would have to combine airflow, poor airflow, and poor water flow. And we have done that with SV Flux and SV Air, which are included in the SV Enviro package offered by Bentley. I mean, that's a way of answering that here. How to couple soil structure interaction with the atmosphere conditions in numerical modeling of unsaturated soils? A great question, because the atmosphere controls how much actual evaporation happens. A lot of times in seepage modeling, we just model a certain flux condition or we model potential evaporation, where what you really want to do is model actual evaporation. What we do is in SV Flux, we implement the Wilson-Penman method of estimating unsaturated actual evaporation from the soil surface. And so there's a method of calculating actual evaporation in there. Another question here, do you suggest providing a cutoff to the total suction of the model to limit suction on climatic conditions? Suction due to climatic can be up to 100,000. Yes, We have, I'm trying to remember the detail because we did research on this a number of years ago. And I'm trying to remember all of it here. We did some studies with cutting it off, but we found if we represented the soil water characteristic curve reasonably and the physics reasonably, then we didn't need to cut it off. You can get high suctions right on the ground surface, and it makes fine nodes and very nonlinear behavior. So we do have an option in the software to limit suctions near the ground surface. Hello, can we include the spatial variability in SV soil as suction can be changed within the soil structure due to soil heterogeneity? Well, you can include spatial variability in SV slope, which is the slope stability software. And so that can be accounted for quite well. And we've got random fields, or I think is the main method for including spatial variability in SV slope. So the answer is yes, you can do it, and you can do it quite easily in SV slope. I didn't have a time to show that, but we can show that if you drop me an email, I can walk you through how that was done in the software. So next question.
So this one is from Lowell from UITM Malaysia. Can SV soil software simulate infiltration?
Okay, so just as far as clarity on software, SV soil is our software that estimates unsaturated material properties. If you want to do infiltration, groundwater flow, that's SV flux. If you want to do slope stability, that's SV slope. And then in Bentley, you can also use Plaxis with the shear strength reduction to do slope stability analysis as well. So really what you can do to do model infiltration very easily is in SV flux. And you can analyze that condition very easily, take into account unsaturated soil mechanics and full climatic conditions, actual evaporation and everything with that. So can we simulate collapsed soils in SV soil? And so right now we don't. That would be a stress problem, combined stress, and that would be SV solid, but which is another finite element problem. We cannot simulate collapse mechanism in SV solid. What I would look into in that case is Plaxis might have facilities for modeling a collapse mechanism, type of mechanism in that case. They have more advanced stress deformation analysis in Plaxis. Yeah, they're like when I think of coupling, I think of it in terms of rigorously coupled processes. So right now, SV flux and SV solid, we use a different finite element solver than Plaxis does. So they're not coupled, but what we have done is to integrate the software is now you can transfer geometry between the packages in 2D. So for example, you can do a SV slope stability model and then import the geometry into Plaxis and run it in finite element shear strength reduction to do slope stability analysis or deformation analysis for that matter in Plaxis. So you can exchange geometry between the packages in 2D is where we've gotten so far in the integration. But in terms of rigorous coupling packages, Plaxis has quite nice and quite extensive coupling of processes, you know, like flow and stress and seismic and stress and that kind of thing. And SV Enviro and SV Flux and SV Solid have their own coupling to do consolidation. And SV Enviro does coupling to do, for example, flow of water and thermal and water, thermal and air, and then contaminant transport and flow. So those types of processes. So each suite has its own detailed coupling, but now you can transfer geometry between Plaxis and the Soil Vision software, which makes it quite a nice overall Bentley environment to work in. Yeah, I think there's a lot of ongoing research on that. I mean, really between the two, I mean, this is I don't consider myself a discrete element modeling expert, but like if you, the big difference, as you know, is discrete element method models every particle, so it's somewhat limited on scale. So you can model very intricate interactions up to a certain more of a laboratory scale. Finite element modeling is more field scale. And I think the research is ongoing on terms of what applications we can successfully model with each method. I mean, like parallelization is opening up new facilities and abilities to process these, either it's discrete element or finite element, on a far faster way. And as such, as the speed increases, then we can utilize these tools to model commercial type of industry problems on a better, in a faster way. So I think research is ongoing with DEM, and its application is proven on certain areas, and it'll increase in the future. Is that maybe a better, a particular answer?